most important part of this talk is or the most, how to phrase it, the most original is the so-called spatial access method object I have implemented in order to do this. Now, this is the Chicago area. I have around probably 100,000 line segments, so I'm not plotting all of the line segments. In this plot, I have sampled, say, around 10,000, and I have chosen the long words, the long roads to be plotted. Now, what this locator point does is that when I move around, you kind of see this zooming of the zooming around the locator. Now, what is going on here? It's basically I'm using this spatial access method object to restrict from the point of the locator to find a little square which is, say, 1 mile long. So I'm sampling this graphic data, which is hundreds of thousands of geometric objects. I'm sampling it in order to produce this graph on the right. Now, the general question is how we find a route from one point to the other. And the way I would resolve this, it's what I was showing here. For example, this guy who is somewhere here in this blue point and wants to go to any of these red points. In order to do that, if you try to build a graph for the whole region, that's a really big graph. So it's computationally quite expensive to do shortest path algorithm. And imagine you want to do this on a large scale with multiple users and to handle lots of users per unit of time. So in order to do that, we basically, the approach here uses what people do. You try to find the highway network, and you're trying to see how you can reach the highway network from your current location. So the lines in red, this is the highway network I have extracted from the data I have. And basically, when we go to that, so let me show you in a different demo here. So if I generate some random points and I do calculate the path and I plot it, so what is happening is so the coarse network is here. Where is the red line? But I need to be able to reach that red line from the destination or the origin. The destination is in blue. I'm sorry. So sorry, the destination is in red. The origin is in blue. So in order to do that, I need to have this spatial access method technology, which samples the geography around the origin and destination points, computes a new graph, and applies the shortest path algorithms in this small graph. So how is this whole thing working, and what are the challenges, and how is going to be developed is what this talk is about. So let me start from the very beginning. I'm going to explain some of the data structures involved, and as I said, the algorithm is basically split in two parts: finding routes through a coarse network and finding paths through a limited, smaller, localized graphs. And the spatial access method, I already kind of give an introduction. So a very important part of this, as I said, the important part is the spatial access method. So after I take the data, let me see, I don't see it in this slide here, so I guess I have put it in a different slide. All right, so maybe, I'm not sure how good this internet connection is, but basically, so there's, you see, I just downloaded from the web the Census Bureau, US Census Bureau data about Illinois, about Champaign, Illinois. This is similar to a zip code. It's called FIPS. It's some kind of new standard for classifying counties and stuff like that. So I have taken data from this source, which is curated, universally worked on. So after I take the road the network the road network data, I do a procedure which I need to do some sort of reverse indexing. I need to be able to access very quickly the geometric objects in that road network. And so in order to do that, I'm going to explain how this is happening. I need to do some reverse indexing, introduce some basis functions, and so forth. What this object, after its initialization is used for, is to do the window queries, which I already demonstrated, and also to do some queries like find the closest path. Sometimes the point you're located at is not close to any road, so sometimes you might want to know what is the closest road to where, say, your car, where you are at. And so this is this kind of functionality which uses the window query. All right, so this is a fragment of the Chicago area. So the bounding rectangles were given here in blue, and in orange I have put some geometric object which corresponds to it. So if I can do this for all. I'm doing this for all objects in my data, right? So if we don't look at the lines, if we just take the geographic objects and we introduce this uniform cell partitioning, these cells they have certain, I know where is the center, where the coordinates. For each of these cells, this is my coordinate system in a sense. Each of these cells is a new vector in a coordinate system. And I'm trying to see which of the rectangles, of the bounding rectangles, intersect with which of these cells. So basically, I have some data structure which looks like that. I know for a given cell which bounding rectangles contain it or intersect with it. So after that, I would, if I have some window query, this is the area which I want to query. I look into what squares, what of the basis squares belong to this window area. And in this way, I can very quickly find which bounding rectangles intersect this green window query area, and I can find all the objects, geometric objects, which which are interesting for whatever we'll be doing with the window query. This is actually quite fast and eliminates the complexity of the spatial which comes with the two coordinates. So after I have found after I have made my window query in which I have found the geometry, and this is exactly that. So I'm speaking now for this area here. This area here is named in this slide area BI. It's like bounded rectangle. So I can produce a graph, and this graph here corresponds to this area here. And this weighted graph, I'll be using it later on to find shortest path between the nodes within this graph. All right, so now the question is, how do we produce the coarse network? So if I return back to my Champagne data example, so.
Don't forget the dinner tonight.
Yes. Yeah. Yeah. I'm going to that too. So this is the third component which I'm going to present, how you hook up this to a natural language processing parser and you get the results interpreted. I did not do the Wolfram Technology Conference. I did beer places and pizza places, but one of the pizza places is Jupiter's is in the list or whatever, so it might be there. Anyway, all right, so in this plot here, I need some way to extract the highways. For those of you who live in Champagne area, these are the, this is, I think this is I-57. I'm not entirely sure. This is probably 74, or probably this is 74 and this is 72. Something like that, whatever. So in order to do that, I need to, there are several ways to, basically it's all heuristics, but what I'm doing is I have some pattern matching, and I'll show it's a very simple pattern matching. I'm looking into the names which came from the Census Bureau of Data. I'm looking for the name expressway, highway, parkway, whatever, state road, and so forth. Now, I have lumped all these major roads together, but ideally, and this is actually in the to-do list, you would have several coarse networks, not just one. You'll have, say, the highways, which allow speed above, say, 65 miles per hour, and then you'll have lesser roads between 45 and 55, and so forth. I'm not doing this here. I basically separate the routes into high-speed routes, low-speed routes. And anyway, now, so after you have found some of the routes, okay, so basically what you get, unfortunately, I forgot to put it in here. Well, let me show you. You get something like this, which is a little bit disconnected. You see, like, say, this area here, and this path, this is kind of important. I want, it's basically this turn here. This is the Chicago area from the airplane. It's basically this turn here and this route here. So you don't, you know, I'm extracting the major roads or whatnot, but you see, they're not well represented. You know, oh, sorry, it's here. It's not well represented. You know, this is disconnected. So you need to find a way to connect to it. And you know, we can take several approaches. You can take all segments which have at least one point to the coarse grid you have extracted. Then you get this kind of nice looking fuzzy extension, but that has it's all connected. Unfortunately, it has too many nodes. And that actually becomes a little bit counterproductive when you try to, you know, you want to speed up, you're using the coarse network to speed up your computations. So this is rejected. Similarly here, a different technique, this is rejected. And this is kind of the winner, which it's not good. And you see you have lots of disconnected components. So in order to these algorithms to work, I need to basically produce a graph from this and find the largest connected component and throw everything out. So basically, I'll be throwing this route out, for example. Now, this is a more of a data curation question, which does not necessarily belong to the whole approach, but definitely have to be solved if you want to use it in a more like industrial or a large-scale setting, you know, more useful setting. So one of the important things is that there are several, as I said, I can use the window queries to find the nearest points in the graphs, but actually using the nearest neighbors with the function nearest in Mathematica, it's a faster approach to do that. And just because this is a non-geometric, this is point queries, and you know, this is a part of the whole thing. And the combination of all parts I already showed when we had this picture here. So basically, yeah, this is my destination in blue. Sorry, the destination is in red, and this is my origin in blue. You can see basically what the person has had to drive to this you know, major road here first, and I have sampled a region around the origin, and I have found the shortest path, you know, around it. So then it's connected to this to the coarse network, and then large part of the trip is over this coarse network. And then when we reach here, we need to sample it and go to the, you know, find a way to our destination. So far so good, and everything is great and dandy. So let's try to see. There's some. Let me see, I should be able to demonstrate this. There's an important thing to consider here, that if you have smaller, this should be a smaller set of points. Maybe I didn't generate the right points here, I'm sorry. All right, yeah, there's some update problem, so I need to reevaluate. If I want to show different set of points, I need to reevaluate. I need to delete the. I don't know why I cannot demonstrate this, but basically, when I have the points to be closer to each other, there is no need to go to the coarse network. I can just sample. Imagine you have from this point where the locator point is, you want to go to here. I can just sample with the spatial access methods. I can sample this part of the geographic data, make a graph, and just produce the fastest, the shortest path. And basically that's it. So anyway, now there is another, further we go with this, is to, what would be the, what would be the natural extensions for this? As I said, definitely better highway extraction. My experiments before coming to this conference was mostly with the Atlanta area. And the Atlanta area, it's actually, the data there is just better or more consistent. For whatever reasons, the Chicago, yes?
What year of the Tiger set are you using?
2010. The 2011, when I downloaded the 2011 like few days ago, I had some problems. There was some mismatching between the names and the roads. I mean, at least for the, okay. So I downloaded probably like half of the counties from Illinois. So initially I wanted to do my experiment with Champaign, Douglas, and I don't know, not Peoria, whatever, Vermilion, or some of the counties around Champaign. But then there was some mismatching, so I kind of moved to this counties here in Chicago area, which is basically Cook, DeKalb, and Will. And again, some of the segments are missing, but so you need to. This needs to be dealt with. There is no excuse, so to speak, not to deal with it. And there are some probably better and more brilliant algorithms than just the simple matching extensions I have been doing. Now, there's a natural thing to do is to actually speed up the whole process by using a grid. So you see the one you can, instead of me producing small graphs by sampling the geographic data, I can just partition the region in this way and pre-compute all these graphs beforehand. Then the question would be, given a point, I need to be able to select one of these pre-computed graphs and just use that for the local destination and origins. I don't need to go through the whole computation and making, so it's another reverse indexing mechanism, but that's actually not that hard to do. And I need to close these graphs because they really put a lot on my demonstrations later on. So the other thing is, how do you interface this functionality to some sort of natural language query interface? For me, ideal end result of this research would be Wolfram Alpha to have some sort of commands like give me all routes between Champaign and Chicago which are within 150 miles, less than 150 miles, or less than 2 hours and a half. Or if you have, you might want to, given the weather conditions, you might, or time series analysis, you can actually try to minimize, from prior experience or whatever, try to minimize certain things. Like, you want to drive from less rain, less traffic, or something like that. So one way to do that is to, this is impossibly many parameters, but one way to do that is usually it's to produce a language, and this is here, I made a parser for like this simple language, which basically understands this kind of sentences. Find routes from here to beer places, give all, routes from where I am at to pizza places or to museums. And so this is actually a very elegant approach. So you see the way this parser is implemented, you see this, I cannot see it here myself. All right, so it's here. This is the interpretation of the origin. So let me do this. All right. So let me redefine the parser. Now you see, when basically the sentence, when we're parsing this sentence here, I'm throwing away in the find routes or whatever. Just the important thing is the location specification. So I know where my origin is, and I know where my destination is. So from beer places, I'll throw away the places, take beer. Because beer, pizza, and museums are the significant component. Now, these two parsed elements are going to be given to the route request function. Now, if I program my route request and my origin functions the way I did them here, so here, origin here, I have hard-coded it with some points. And if my destination, fun, near pizza, and so forth, they actually randomly generated points. So I cheated when I told you, or lied when I told you we'll find champagne, Jupiter and stuff. But principle is exactly the same. From beer, you need to find all the points of interest which have the tag beer or the tag pizza, and they're relatively close by air distance, which is fast to compute. Then you just give it here and you find the routes. Now, the other thing is I'm also computing. I cannot slide down. I'm also. Well, on my laptop, I can see this, but basically, I'm also programming an interpretation of this route request. And you can see when I have parsed the results here, I get the parsed results, and I get this. So you see how this plot is organized? It's basically a parsed results. The result of this parsing is this plot, which gives you the routes from the origin point to the destinations given. All right, so instead of giving a summary to recapitulate, I had, this seemed like very simple, relatively simple idea. It's basically what people do when they try to find routes to places. They'll take the map, they'll try to figure out which highway to use, and then how to go to the highway and how from the highway to go to the actual destination. So I've been programmed exactly that. If you're using if you're preparing a graph for the full set of geographic geographic data, that would be too much of a lot, and you cannot answer that many queries. With this approach, this is greatly simplified, and you can see when Google Maps or Apple Maps, they actually use the same approach. When you kind of give them a distance larger than, I say, 12 miles, they'll be not using local finding of the routes. They'll actually try to find a coarse network and go over it. So I had to resolve a variety of things. So the most important question after extracting the highway is how do we, the calculating of the coarse network after you make the graph, this is easy. But how do you deal with the destination origin point to the coarse network? How do you deal with that? You need to have fast way to access it, either by pre-computation, which I suggested, or the way I'm doing it right now, which is on the fly. And third, for me, it was very interesting just, because my previous talk in Accelerate session didn't go that well for the parsers, I decided, okay, I'm going to do this for this talk. This actually, it was relatively easy for me to program because of the parser technology I have at hand, but this is actually the end game, using some sort of interface to kind of specify different scenarios here. All right, thank you for your attention. Yeah.